Okay, guys, so let's get started. So first of all, we talk about the quiz, the modeling, answers modeling. If you have, what I need is that the report, okay? The report and what I needed and has been written clearly in the report, the figures, the deformation, the figures, and also the tables. In addition to this report, I also needed to, I need you to give me the standalone, the answers modeling files. That means I can check your modeling on my computer. Okay? So if you have not given me the standalone files, and you need to give me by this Friday, which is our due date. Any questions regarding the quiz one now? Also, and for this midterm, and I told you guys we do for the midterm. If you that I told you guys that is optional also. If you want to improve your scores, you can just work on the problems that you have lost the points on, and then you can get 50% of the points back. I think this is a very good way to improve your final grades. Also, as I said, that is the optional. If you think it's not necessary for you, and I'm okay. Okay, I will not force you guys to do anything. Without further ado about the midterm and the quiz, and we are going to continue our talk of this is the cleavage. Also for the cleavage, we have talked about we have three commonly used this is the splitters. One is the BCC, and one is a BCC. One is a BCC, and one is FCC, and one is HCP. So they have this is if you have taken this material science, and you should have better understanding of this what is the FCC is. In case of this one we talk about, okay, so the propagating crack changes direction each time it crosses a grain boundary. The crack seeks the most favorable oriented cleavage plane in each grain. So this is understandable. The cracks always go to the most vulnerable these spores, because it can use small energy to just facilitate the crack propagation. So this is a BCC. FCC cleavage is most likely when the plastic flow is restricted. Okay, if the plastic flow is restricted, we have cleavage. FCC metals are usually not susceptible to cleavage because there are ample is a slip system for ductile behavior at all temperatures. You should know what is a slip system is. Slip system means that in which direction this is the break is going to occur. At low temperatures, BCC metals fail by cleavage because there are limited number of active slip systems. Because if the number of active slip systems, so it can have no chance to sleep. Sleep, as the name suggests, sleep means they can just have some dislocation. If there is no dislocation, systems, and then it will cleavage. So FCC is closely packed. Okay, you can see FCC is closely packed, and they usually have 12 slip systems. 12 slip systems, that means if there is loading, if the loading is increases, they have 12 slip systems to release the energy. So that's the reason FCC usually do not have this cleavage, and BCC usually has. So the third category is HCP, hexagonal close packed. So this is a typical one is zinc. And this guy has 3 sleep systems per grain. And we know that because when we compare this guy's number of sleep systems with those of FCC, it's 12. It is much less than 3 is much less than 12. You guys agree? So as a result, HCP are more susceptible to the cleavage fracture. As I said, the more sleep systems, the more likely that the ductal plastic deformation occurs first. So this is 3 different categories. So this is a figure 5.18, okay, not 18. And this is a 5.18. Can you write down, guys? I did not copy the figure here. This is a figure 5.18, and this is chapter 5, the number 18. And this shows SEM. SEM is scanning electron microscopy. The fractal graphs of cleavage fracture in a low alloy steel. The multifaceted, and you can see the multifaceted surface is typical of the cleavage in a polycrystalline material. Polycrystalline means that we have multiple grains there. So each facet corresponds to a single grain. So the river pattern is just like a river. On each facet are also typical of cleavage fracture. And these markings are so named because multiple lines converge to a single line. And so this is look like the tributaries to a river. Have you guys see this is a lot of tributaries and they just converge into a river? I will see this is a Google, this is a geography. For example, Amazon River, you can see a lot of very, very small rivers, they converge into a bigger river. Also, in the Africa, this is a Nile River. And also in China, this is the Changjiang River and also Huanghe River. We have this kind of the pattern. The small rivers converge into a bigger river. So this is very like this is a river patterns. We call it river patterns. So a river pattern means this is a cleavage, right? So for the ductal surface, when the ductal surface the ductal surface the color is a green color. However, for the brittle surface, some areas they are very shining, so other areas is are dark. Right? So this is dependent upon the material. So here are the mechanisms of cleavage initiation. How is the cleavage initiated? And so here are 3. So first one is the sharp micro cracks. If there is a sharp micro cracks, and so if you apply the load, you improve the loading, and so you might have is a cleavage. Okay, as I said, cleavage means that there is an existing sharp crack, and then you just improve the loading, and then the crack grows until the whole specimen the fractures. So second one is illusions. Illusions means that within this is the material, this is the matrix material, and there are some very, very hard second phase the particles, and all other very, very hard particles. So these hard particles, they are treated as inclusions. So this inclusion, because this is inclusion, right? Usually this, if something happens, these inclusions, these hard particles, and they separate from this is a matrix material, and they will gap, and then you apply load, and then this cleavage will occur. And the third one is second phase particles. So second phase particles, actually, it is another kind of illusion. Second phase particles means that this is the same material, but usually this is because they become a compound. So this compound and chemically they are different. Chemically and physically they are different from the matrix material. So this is called second phase particles. So here is one example if the particle is spherical, and it produces a penny-shaped crack, and then the fracture stress can be written using this equation. So this is called the Griff type. So sigma f is a failure stress, and failure stress it is written as the pi Young's modulus E, the gamma p. Gamma p is the plastic work per unit area required to propagate into the adjoining the grains. Keep in mind. So this is the P means the plastic work, and so P with gamma P and gamma S. Gamma S is the surface area energy, we know that, and usually so the gamma P is far larger than this is the gamma S. Right? So gamma S is the surface energy the material needs to overcome in order to produce a crack. And C0 is a particle diameter, and C0, and nu here is a Poisson's ratio, and I've looked for this model, okay? For this model, if we have this is yield strength, that yield strength equals 400 megapascal, Young's modulus 210 gigapascal, and the gamma p, and this gamma p is the plastic work per unit area required to propagate into the adjoining grain. If we can specify this one as 14 joule per meter square, and then we just substitute all these guys into this equation, and we can just set the failure stress equals 3 times the sigma ys, and then we can calculate this is a C0. I'm sorry guys, so here is a typo here, and write down as. Here is not sigma 0, it is a C0. And C0 is the particle diameter, is a critical particle diameter that can cause this is the crack. This is a C0, right? This is a C0 here. C0, not sigma 0. I just C0 equals 7 micrometer. 7 micrometer. So this is the Griff type. So this is one model. Another model, and here is a Smith. The Smith proposed another model in this model, and the Smith took care of the dislocation pile up. You guys know dislocation, right? You know the dislocation, the pile up, and they just this equation, they use this equation, and you can see, C0 is still, so this is a particle diameter, and sigma f is a failure stress, and the ky here, ky is a pile up constant, and this is material dependent. If you have a material, and you can just check the literature, and you might have get this pile up the constant. And this tau I is a friction stress. In order to move a dislocation, the energy you need to apply. Okay, so this is the tau I. We also have this tau I and tau y. And tau I is a friction stress, and the ky is a pile up constant, and the d is the diameter of the grains. Can you write down it? The d is the diameter of the grains. So this is tau y. We can use this equation to calculate tau y. Tau y is yield strength in shear. And what do we call this equation? So this equation is called the Hall patch equation. This is tau y tau y equals and tau I and plus ky and d and power 1/2. 1/2. So this one is called Hall patch equation. Have you guys ever heard this equation? So this equation, you can see. So this equation, and based on this equation, and what conclusion you can get? Can somebody tell me? On how this tau y is dependent upon this the d, Bobby. What's the relationship between the we call the average, the grain diameter, and this is the tall one.
It's inversely squared. Okay.
Inversely, right?
Yeah.
Inverse, that means the refined the grains, usually we will get on the higher yield strength. Okay, right? Yeah, this is true, okay? So some researchers, they use the different strategies on one to just refine the material of the grains. Alright? Why? They want to improve on this yield strength in the shear. Any questions regarding this equation? No questions? Okay. You don't need to memorize this equation. Okay. What I need you to do is that if I ask you, and you know what it is. So based on this equation, what we want to do, and we want to calculate on the sigma 0. And sigma 0 is a critical diameter of the illusion of the particle. And this loading condition, what is the particle diameter that can cause the crack to propagate? Definitely this is a model, okay? Questions so far? So when sigma 1s, yield strength goes up, and cleavage is easier to happen. Why this one is true, guys? Can somebody tell me? Sigma 1s is what? Is the yield strength, right? So if this yield strength is very, very high, that means before the material yields, it is still the elastic, and then the cleavage happens. Right? If the yield strength is low, that means after you apply the load, the material will go to the plastic deformation first. And the plastic deformation usually just stop the cleavage. The cleavage happens. Questions? No questions? And we talk about these two models. And then there are some unsuccessful cleavage. That means sometimes the cleavage, they will not go through from very beginning to very end until this whole specimen fails, because it is a bigger single crack. And sometimes there are three case scenarios. First one, the cleavage is arrested at the particle matrix interface. The particle matrix is the major material. Particle is just some particles here. The second one is arrested at the grain boundary. So cleavage is arrested at the grain boundary. That means at this time, the crack cannot go through because energy is not high enough. A third one is arrested at the stress gradient, and due to a steep stress gradient. Do you guys know what is a gradient, guys? Whenever a gradient comes to your mind, and what comes into your mind? When you see gradient, what comes into your mind? Bobby?
Like a change across a parameter. I mean, personally, I think of like a color gradient, like the color kind of slowly changing.
Yeah, change with respect of what?
Certain parameter, either time or distance.
Yeah, distance. Okay. The gradient usually we talk about the stress gradient means that high stress gradient means that in the neighboring locations the stress changes very high. So this is called high stress gradient. And there are several models here. First one, mathematical model of cleavage fracture. Okay, so here is a crack. And so this is the 3 genii, and propose this one for us. Is Ritchie, Knott, and Rice. And Rice is a very, very famous guy. And so it says that the sigma at xc at the critical equals sigma f. F is a failure stress. If this equation is satisfied, cleavage will occur. You can see here's what is xc, and xc is usually about 2 grain size. Right? 2 grain double of the grain diameter. So this is XC is a material dependent parameter. Definitely, different materials, you have different grain size. Also, even in the same material, if these specimens they have gone through different processes, and their diameters are still different. Do you guys agree? Okay. So here is one model, and second model is called the Curry and Knott model. So this one is a statistical model, right? Statistical, and a sample. This is a sample. Sample means we have a bunch of things. A sample volume over which sigma y and in the x in the y direction. So this is x. So this is y, and sigma y is greater than sigma f, and so this one is satisfied. So cleavage fracture toughness. Okay, cleavage fracture toughness, and usually we use large scatters. This is small. This is specimens, and cleavage as a weakest link phenomenon. Right, cleavage. So look at this figure. So this F is a probability of sampling one or more critical particles probability, and 1 minus exponent E minus PV, and P is here is critical particle per volume. It depends on the stress level, and V is the total volume sampled. And we can use this equation, right? So this is we take this equation, and we have this is 2 parameter the Weibull distribution. This F here, and so we can see, and so this one we can just use this one to be more specific. We have equation 527a. So here, right? So this is power 4 is a Weibull slope. You know, you have learned Weibull distribution, right? Yes, Weibull distribution or Kappa distribution are different distribution, and that is the statistical concept. And sigma k is a skew parameter, right? And sigma k and sigma j. So here this one equation. So this is a second equation. And sigma k and sigma j are material parameters that depend on microstructure and temperature. And slope is a measure of relative scatter. So the problems. So there is a zero threshold. There is no threshold. And second one is larger scatter, and then the experiments. So you need to do a lot of experiments to get a scatter. And then people find this equation, truncated Weibull, and to use this one to solve these 2 problems. You can see the difference between this equation and these 2 equations. If KIC is greater than K0, and K0 serves as a threshold, and they just put the threshold. If KIC is greater than 0, we use this one. If KIC is less than K0, and we use F equals 0. Right? So for the 3 parameter Weibull, we have this one. We have K mean theta K, KIC is called the 3 parameter Weibull. K mean Weibull location parameter. So this is dependent upon what kind of parameter you are using. And for this is crystal, we have single crystal, we have polycrystal. So single crystal means that no boundary, no grain boundaries inside. And we have for polycrystal, and so this is 1 grain, second grain, third one. So this is each of these unit. This is the shapes. They are the crystal. So we have polycrystal. Polycrystal, you can see we have this is boundary, this is grain boundaries. So this is grain boundary, this is grain boundary. So many grains. They have interior of grain boundaries. Grain size is usually 10 micrometer to 1,000 micrometer. So these are the 3. These are several models about